Welcome back, guys. Good morning, good evening, and good afternoon. This is a continuation video of our friction section. So, before I gonna go to example number four, I'm just gonna discuss quickly that there are two types of friction. Uh, we have what we call static friction, and the other one is the kinetic or sliding friction. So static friction is the friction that exists between an object and the surface when the object is not moving. So an example would be if you have a table resting on a surface, horizontal surface, if you're gonna apply a force, let's say you're pushing it to the right, you need a certain amount of force before you can move it. So let's say for example, if you just push it with a minimal force, it will not move. The reason for that is the static friction. And before you can move that particular table or object, you need to overcome the maximum static friction. So static friction is not fixed. Um, it's just, and it will exist once you apply the force um, in a certain direction. So the other type of friction is kinetic friction. Well, once you overcome the static friction, now when you can move the object, even though it's moving, there's what we call a kinetic or sliding friction that exists between the object and the surface. And if you're gonna try this one out, it takes more force to start an object moving along a surface than it takes to keep it moving once it has started. That's the reason why, well, coefficient of static friction is always greater than the coefficient of kinetic friction. So we're gonna go directly to example number four. By the way, if you're asking for uh, the expression for static friction and the kinetic friction, it's just uh, the same with the friction expression. Um, it's just that for FFS, well, it is the volume in between should be less than or equal to mu s times the normal force. So Fs stands for the coefficient of static friction. And kinetic friction, on the other hand, is given by Fk, which is equal to mu k times Fn. So again, mu s and mu k are dependent on the type of surfaces in contact. So let's move on to example number four. So a force of 500 Newton is used to push a 200 kilogram box along a surface that has 378 Newton frictional force. What is the acceleration of the box? So again, I'm just gonna take note of the given quantities that I have. So this would be the applied force. So you're gonna call that one as my FA. And I have a box that has a mass. So remember that this is a mass because of the unit of 200 kilograms. The unit is kilogram. So that's what I know. That's why I know that it's a mass. And the frictional force is given with a magnitude of 378 newtons. So this is my F. And then I am asked to solve for the acceleration of the box. So again, uh, to start with my solution, I'm gonna start with the free body diagram of the box. So it's always good to have the diagram because it's much easier for you to identify, well, again, what particular Newton's law you're going to use. And again, it's always good to see the forces acting on your object. So if I'm gonna identify the forces acting on my box, I have the weight, that is Fg. I have the normal force, Fn, which is upward. And then let's say, for example, the applied force is to the right, and that is 500 newtons. So if the applied force is 500 newtons to the right, it must be that the frictional force is to the left. So my FF would be given as 378 newtons. So what is the acceleration of the box? Well, in this particular situation here, I know that my normal force and the weight of the object would have the same value. So there's no movement vertically. So it must be that the normal force is just equivalent to the weight of the object. So the motion of the object would just be based on the diagram that I have, the free body diagram. It must be that the motion is just along the x-axis. So if you can see here, FF and the applied force are not equal. So therefore, the object must be accelerating to the direction of your net force. So I can use that the net force along x would just be equivalent to the mass of the object times its acceleration. So remember that the acceleration that exists in this particular case is just along the x-axis. Again, normal force and gravity have equal in magnitude, so therefore the acceleration along y, or the vertical acceleration, is equal to 0. So the acceleration is just along the x-axis. So that's given by the forces along x is given by Fa and the frictional force. So the forces along again along the x is given by Fa plus the negative of F. And again, the net force is equivalent to ma. Again, this is according to the second Newton's law. Remember that if you have acceleration, the magnitude or the net force is just equivalent to the mass of the object times its acceleration. So Fa is given as 500 plus FF is negative 378. And that is equal to the mass. The mass is given as 200. And then the acceleration is unknown. So you have here 500 plus the negative of 378. That gives me positive 122 is equal to 200a. So solve for a, that would be divided by 200 divided by 200. The acceleration is plus 0.61 meters per second squared, but in one significant digit, that would be positive 0.6 meters per second squared, or again, positive is to the right, so you're gonna write 0.6 meters per second squared in the right direction. So again, it asks for the acceleration. So acceleration is a vector quantity, so you need to specify both magnitude and direction. So again, just a quick recap. Your solution should start with a free body diagram, and then you try to identify uh, which uh, which of the Newton's laws you're going to use. Again, we have the first Newton's law and the second Newton's law. The first Newton's law tells you that the object is at rest or moving with a constant speed, so you use that one. And if the object is accelerating, you use the second Newton's law. So I can assign you example number 5, 6, and 7 as a homework, and I will be checking your solution. And so I'll not be looking at your final answer, but I want you to follow the uh, the solution in which you start with the free body diagram. So I'm gonna check your solution with the proper assignment of the different forces, as well as you always start with the uh, equation that you use. So I will not be checking your work just based on your final answer. So I'll be checking your free body diagram, and then next your starting equation. So which particular uh, equation you use, and then before you substitute with the numbers. So again, uh, make it a habit to start your solution, especially for the dynamics part, and it could also be useful for uh, any later discussion. So it's always good to show your solutions properly. So again, just even though it's quite obvious, so don't start with the numbers right away. Try to show your work properly. So yeah, I will be giving you time to work with example 5, 6, and 7. And and yeah, I'll be posting the answers as well as uh, the sheet for the friction lesson at the end of the week. So I'll be posting a Google folder in our Google Classroom, wherein you can send your answers. Again, you can write your solution in a piece of paper and take a picture of that and submit it in the Google Classroom. Okay, and if you have any questions, just send me an email. And have a nice day and keep safe, everyone, and follow the advice of our health official. So practice social distancing and wash your hands properly and stay home. Thank you and God bless everyone.